I'm going to discuss the concept of a sampling distribution of a sample proportion. This begins with a binomial distribution or a binomial situation. Basically, you have a probability of success and you collect a sample, or you repeat an experiment n times. In this situation, you could think of it like rolling a six-sided die and looking at one of those sides as your desired outcome. For example, rolling a 1. So I would roll a 1 0 times out of 10 with a likelihood of about 16%. The most likely outcome is one roll of a 1 in 10 with a 32% chance. So you can kind of see how that would be affected with different n and different p. But I'm going to show you how we would turn this into a sampling distribution. So the first thing you'll notice is we talk about the point estimate of sample proportion. That's x out of n. So instead of thinking of it as just how many do we have, we're going to think about it as what percent of the sample is the desired outcome. So this would be 1 in 10. This would be 0 in 10. That would be 0% of the sample results in a 1. This would be 10%. 1 in 10 is 10% of the sample is a 1. 20%, 30%, and 10 out of 10 would be 100% of the sample. That's what a sample proportion is. So using this applet, I can kind of show you what that would look like. What I'm going to do is kind of draw samples one at a time. And instead of rolling a die, it's kind of using this spinner wheel to simulate that roll, with the small slice being about 1/6 of the total. I did have to round it. So in this first simulation, I got a 1, or my desired result, 1 out of 10 times. That's going to plot a 0.1. And I can flip it over to see it with the x-axis, but I'm going to use the p-hat axis. Okay, so I'm going to draw another sample. I don't need to continue to see these. In the second sample, it was 3 in 7. Now that's a little small. Let me kind of make that bigger here. So 3 out of 7 times is 30%. So I'm going to continue to simulate 10 rolls of a six-sided die and see how the numbers stack up. Let's go ahead and just do 100 real quick. So I've drawn 145 samples, and it looks pretty much like that binomial distribution. So this is not yet a sampling distribution. With a sampling distribution, you have some properties and requirements. The first requirement, the biggest one, is that n times p times 1 minus p has to be at least 10. Now I know my p is 1/6. 1 minus a sixth is 5/6. So those are complementary probabilities that add to 1. Kind of like 50-50, 40-60. Just remember, use decimals for percents or use fractions. So that's 1/6 times 5/6. If I divide that from each side, I can figure out what n I would need. So I have that here. 10 divided by 1/6 times 5/6 is 72. And if I roll a six-sided die 72 times, I would expect to roll a 1 1/6 of that, or about 12 times. So you can kind of think about if I move this to 72, what that would look like. It's starting to already look more like a bell curve, and that highest value should be 12 in 72. So that's good. Let's go back over here, reset, and now take 72 at a time. And I'll just draw 100 right away. So that doesn't really look like a bell curve. The thing with the sampling distribution is we would need to see every possible sample, or we would need to simulate it lots of times. I'll set it to 100,000. I clicked it a couple times, so we're over 200,000 samples. That looks like a bell curve. There are some spaces in there. You can't get to every possible percentage. Think about like if you're dividing by 50, then you'd only get down to every other hundredth, like 0.02, 0.04, 0.06. If you had 100 in your sample size, you could get down to the hundredth, 0.01, 0.02, 0.03. So you will naturally have some gaps in there, but you do have this very predictable bell curve. From there, you can calculate probabilities. The way you do that is you use the population proportion for the mean of your sampling distribution. My population proportion is 1/6, so I would expect my samples to average out to be 1/6 after multiple repeated trials. The standard error or standard deviation of the resulting distribution is found by the square root of p times 1 minus p divided by m. So kind of some parts of that, just a little different arrangement. And one other note, if you have a finite population, for example, if you're looking at voters, you always want to make sure you're not sampling more than 5% of the population, because then you'll actually start to change your probabilities, kind of like if you're drawing cards from a deck without putting them back. So that's something you might have to check as well. Mine is a dice roll. It's not a finite population, so I don't need to worry about it. So now I'll go to StatCrunch, stat calculator, normal. The resulting sampling distribution will be normally distributed with a mean equal to p hat. That's 1 out of 6 or 0.166, however many you can fit. I'm going to just shorten it down 0.167. And for the standard deviation, I'll go to my calculator and find it that way. So it's going to be the 1/6 and the 5/6. And then all of that is divided by n of 72. That's about 0.044 for mine. Real rough rounding, but that's okay. Now I can draw the curve. The highest point happens about 17% of the time. So there you can see my first, second, and third standard deviations on either side. So let's say I roll the die 72 times and I only get the one, let's say under 5% of the time. Now I can figure out the likelihood of that range of outcomes. So that's going to be very, very unlikely. This by itself may not be super helpful. We can talk about, how a sample looks compared to other samples, but really it starts getting a lot more useful when we move forward and find confidence intervals and do hypothesis testing.